Hello everyone, my name is Yuki Endo from University of Tsukuba in Japan. Today I'd like to talk about controlling StyleGANs using rough scribbles via one-shot learning. Let me begin with the background. Recent advances in generative adversarial networks is remarkable, and GANs can be used for various downstream applications. Latent code manipulation is one of the image editing techniques using GANs. This technique can edit various attributes like pose, hair color, and age using GANs trained unsupervisedly. For example, as you can see in this figure, the user can edit age by moving latent codes toward specific directions. However, this manipulation is not necessarily intuitive against layout-related attributes like orientation and pose as shown in the right figure. It's also challenging to find latent directions for diverse layout-related attributes using this approach. More intuitive approach may be to use a semantic mask as input. This approach enables specifying layers more intuitively. However, it requires substantial paired training data for high-quality outputs. As you can see, a DNN trained with 20,000 paired images can generate photorealistic images, but a DNN trained with a single paired image cannot obtain such results. Also, fine-grained and pixel-wise annotations using dense semantic masks are costly. In our work, we aim to control GANs via one-shot learning using rough sparse annotations. We term these annotations semantic scribbles. As you can see, the user specifies output layouts with sparse annotations like brush strokes for cat body parts and cross lines for anime portraits. We propose a method that can generate photorealistic images from various semantic scribbles by learning a single paired image. Our key idea is to construct mapping between semantics predefined in a one-shot example and the StyleGANs latent space. To achieve this, we use a PSP encoder by Richardson et al. However, as you can see in this figure, simply training the PSP encoder using a single pair does not generalize to diverse semantic scribbles. You can see output cats are not aligned well here. To solve this problem, we use pseudo-semantic scribbles to train the PSP encoder. From randomly sampled latent codes, we can generate plausible semantic scribbles for StyleGAN images, even if only a single training pair is available. This is done by using intermediate feature maps and inspired by the Collins et al.'s insight that pixels with the same semantics have similar StyleGAN features. Although scribbles obtained by pseudo-labeling are roughly annotated, we can obtain photorealistic images in inference time. This is because the decoder is pre-trained with other large real image datasets. Also, we propose a method for optimizing latent codes to refine output alignment if necessary. As you can see, the latent codes are optimized by minimizing the difference between an output image and input scribbles. Next, I will introduce related work. Again, there are two approaches to generating images from semantic inputs. The first one is a general image-to-image translation approach, such as pix-to-pix and spade. This approach can generate images aligned with given semantic maps, but their quality is bad in a one-shot scenario. The second one is GAN inversion approach, such as PSP and E4E. In the results by this approach, image quality is good, but alignment is bad in a one-shot scenario. We therefore improve the second approach by learning pseudo-labeled data. Recently, several few-shot techniques were proposed to generate semantic segmentation masks for GAN outputs. However, these techniques are not suitable to replace our pseudo-labeling. They do not work in class imbalanced settings where only sparse sets of pixels are labeled. We demonstrate comparisons with these methods later. Now I explain our method. We first confirm our problem setting. Our goal is to accomplish Scribble-based image synthesis. The input is semantic scribbles represented as a one hot mask, and the output is an RGB image. The training data consists of labeled images and unlabeled images. In a one-shot case, the number of the labeled images is 1, and a lot of unlabeled images are available. The overview of our method is as follows. First, we prepare StyleGAN pre-trained with unlabeled data. Then, we sample latent codes from prior and generate StyleGAN images. Next, we perform pseudo-labeling for these images using the labeled data. Then, we update encoder that extracts latent codes using pseudo-labels. We iterate these 3 steps until convergence. Finally, we perform an inference phase, which includes post-processing if necessary. This slide shows our training pipeline of the encoder, and the algorithm is simple. For each training iteration, the encoder is trained according to the following steps. We first randomly sample latent codes. We feed the latent codes to StyleGAN and perform pseudo-labeling using the StyleGAN features. Next, we feed the pseudo-semantic scribbles to the encoder and finally update encoder using this loss function. In the next slide, I will explain the pseudo-labeling. As you can see the left part of the figure, we first extract classified feature vectors f corresponding to each semantic scribble. We then find matchings between the feature vectors and pixels in images newly sampled from StyleGAN. As you can see the right part of the figure, we take the correspondence between f and sampled feature maps using k-nearest neighbor matching to create plausible scribbles. In general, encoder-based GAN inversion I explained so far is fast but not so accurate in reconstructing images. Therefore, we propose optimization-based post-processing to further refine our encoder-based outputs. In our post-processing, we optimize latent codes by minimizing the difference between StyleGAN feature maps and input semantic scribbles. The question here is how to calculate this difference. For this purpose, we exploit Collins et al.'s insight again. We assume pixels annotated with the same semantic scribbles have similar StyleGAN features. However, as you can see, simply optimizing latent codes using this assumption results in almost flat color images. To solve this problem, we exploit the GAN space idea. GAN space is a method that applies PCA to latent space to find latent directions for attribute editing. During optimization, we move latent codes only toward principal directions. This can avoid generating flat color images, as you can see in the right image. Please see our paper for more details of the loss function. Now we can obtain plausible images via optimization, so the next question arises. If our optimization approach works, we do not need our encoder. In other words, can we obtain plausible images by optimizing randomly initialized latent codes? To answer this question, we verify the effectiveness of initialization. In this figure, The first row shows the results from latent codes initialized with average latent codes in a latent space. The second row shows the results from latent codes initialized using our encoder. Obviously, the latter case shows better alignment with the input scribbles. This observation demonstrates that initialization is important because optimization has local minima. Next, I'd like to show experimental results. This slide shows implementation details. I omit details but want to mention computation time. For inference, our encoder-based method takes 0.2 seconds, while post-processing takes 15 seconds. So the user is supposed to first use the encoder-based method interactively, and finally apply post-processing. This slide shows qualitative comparisons. From left to right, one-shot training example, test input, and results by the existing methods and our method. As you can see in the PSP results, it ignores the input layers due to overfitting to the single training example. In the result of dataset GAN and repurpose GAN, we used these methods instead of our pseudo labeling in our framework. As you can see, these methods cannot also sufficiently consider the given layouts. In contrast, our results overall reflected the given layouts. Also, we can see post-processing further improves our results. This is another comparison. Dataset GAN and repurpose GAN relatively works, but some results like these do not reflect the given layout. On the other hand, our method can consider the given layout overall. We also conducted user study. We asked 15 people to score the qualitative results regarding layout faithfulness. As you can see the table, our method outperformed the existing method. Post-processing also improved our encoder-based method. Additionally, our method can also obtain multiple results from a single input. This is achieved by style mixing that feeds different latent codes to shallow StyleGAN layers. Finally, I discuss limitations. First, as you can see in the image B, our encoder-based approach cannot reflect complicated layouts. This can be alleviated to some extent by post-processing, as shown in the image C. Also, as you can see in the image E, our method built upon StyleGAN cannot handle layouts that StyleGAN does not train. Now I conclude our talk. We explored a novel problem of controlling GAN's outputs using semantic scribbles in a one-shot setting. To achieve this, we propose a simple yet effective framework for training a StyleGAN encoder via pseudo-labeling. We also proposed optimization-based post-processing to refine our encoder-based results. Future work is to develop a method for more accurate and fine-grained layout control. Specifically, we would like to use not only sparse scribbles, but also dense masks concurrently. We are also interested in extending recent GAN inversion method and StyleGAN 3. Please try our code, which is available from this URL. Thank you for your attention.